Alright, welcome back to another video by Firestarter Graphics and Engineering. Today's where we get into the fun stuff, the meat and the potatoes of this. And it might get a little confusing, so I'm going to try to type math equations where I can. So I'm going to do it live so that you can follow and see what I'm doing. I'm not going to do too many screenshots, or at least not try to. Alright. Okay, so last time we went over this ranking thing, but now we're going to go over an actual example. So if we take the original equation, let's just go back to the top. This equation that we started with, the fundamental equation, and we rearrange it just a little bit so that we're dealing with a failure. One out of something fails, because that's our ultimate goal. Hey, I want to know what the failure is. Like if I have 2 out of this or 1 out of this, or I can only allow a certain amount to fail. You always want to break it down to 1 out of something. So let's go back down. Okay, so 1 divided by our failure rate. That's usually a pretty good guess. 1 over f, hey, 1 out of 20, 1 out of 30. But we want a little bit more precision. So we do 1 divided by 1 minus the failure rate. It just gives us a little bit more reliability. Okay, so this is equal to e to the sigma f divided by sigma naught to the m. Now you're wondering, where did all these come from? Okay, m is nothing more than the Euler exponent, which is also known as the shape parameter, which is what we went over as beta. Now I'm changing it because in engineering we deal with stresses. Sigma f is a stress. T is a time. So I want to deal with stresses today. Sigma naught, which is our characteristic strength. That is our N. That's the strength at where 63.2% of all of our parts fail. Now there's an easy way, a really easy way to solve for this, and a lot of people just skip over it, including my professor. So I brought it up to him a while back when I was learning this. I'm like, dude, there's an easier way. And when I showed him, he was like, oh, I don't even know why I didn't even think about that. But if you've ever taken thermodynamics, you've looked at steam tables and all these things, and you've had to do a process called linear interpolation. So that's what we're going to do today, is linearizing equations and then linear interpolation. Okay, so we have these equations, these graphs, these Weibull Ernst distributions. They do not look pretty linear. They are pretty curvy, and we all like curves. So now we got to turn these to lines. How do we do that? Well, if we look at this equation, it's definitely not linear. We have 2 exponents. So the best way to deal with exponents is by taking the natural log on both sides to bring them down. And that way we can normalize this equation to some sort of line. So I'm going to go ahead and show you that right here. So I took the natural log of both sides, got rid of the e on the right hand side, and it brought down these 2 exponents. If you don't know algebra, that's okay. Just follow along and it does work out. Okay, now we still have this 1 exponent left, so we got to take the natural log again. Now, if you know algebra, we know that the natural log of something divided by something usually breaks into, not usually, always breaks into a subtraction. That is the rule. In algebra, everything's about opposites. If I wanted to move a positive number to the other side of the equation, I'd take its opposite, or the negative. If I wanted to, if I have a multiplication like 2 times x on one side of the equation and I just wanted x by itself, 2 times x, you do the opposite of the multiplication. You divide by what you're trying to get rid of, which would be the 2. Anyways, so this is what we get with at the end. Now this is in the form of a line. Y is equal to m, then x plus or minus our b, our y-intercept. And that means when all of this is 0, y is going to equal whatever number this is right here. So if I had a line, y is equal to 2x plus 3. If I let x be 0, the y-intercept would be 3. That means that's where the line crosses the y-axis. Okay, so We know that y is now equal to the natural log, this business. M is just m, it's the slope, or beta, or shape characteristic. X is equal to the natural log of sigma f, our testing criteria. And then B is equal to all this business. Okay, that's great. So let's look at this in Excel real quick before moving forward. So I went ahead and did 25 samples on my on a tensile machine at school of PLA plus. Quote unquote, random generator in Excel equals tensile machine, unquote. Okay, so values between 46 and 56. All right, looks good. Went ahead and ranked them from smallest to largest by using, where is it? Data, and you can sort, I think it's this one. Lowest to highest, yes. And it sorts it. Then I put the rank number 1 through 25. Now, since I'm using more than 10 data points, I'm using the standard failure method right here. It's just pretty straightforward. It's pretty accurate. And that's what is right here. And you can see the formula up here in Excel if you want to pause the video. So what this is telling me is, hey, if all my parts are designed to handle, I'm making a hook that holds a coat. And it can handle 46.1 megapascals. I'm only going to have 2% of all my product fail. So if I make 100 of these hooks, 2 of them are going to fail. So 2 out of 100, not bad, if I keep the limits to 46.1. And it goes higher and higher, and as you get higher in your strengths, obviously your failure rate is higher. Okay, so earlier I mentioned this characteristic strength N, or sigma naught, or eta, which is N. And it's where 63.2% of all the parts fell. If we look at our data, we have 62 and 66%. There is no 63.2%. But luckily, we can use linear interpolation to help us solve. So how do I do that? Well, there's a math formula for it, and it's not too bad, but you can use an online calculator. So let's go ahead and look at that. So linear interpolator, it's a calculator. Okay, so I'm letting my x values be the megapascals of strength. I don't know what this middle one is, but I know what my percentages are. So those are my y values, and I hit calculate, and 52.22 megapascals. So if my product is designed to handle 52.22 megapascals, that's the characteristic strength, sigma f or N, where 63.2% of all my parts will fail at this strength. Okay, that's good to know. That's really good to know. Now, what's the other method of solving for that? Let's open up our notes. We know that the y-intercept B is equal to all of, well, we know it's equal to all of this business right here. We know that. Okay, so what that means is now B is equal to negative m natural log of sigma naught. We need to solve for sigma naught. So when we do that, we get sigma naught is equal to e to the negative b over m. B is not beta. That's just your y-intercept. That's just what it's called in math. So you got to keep track of B, 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 and B, and B, because sometimes B is beta, sometimes it's not. And sometimes beta is not beta. Sometimes beta is another beta. And it gets all confusing. So if you haven't taken strength and materials, or you have, you know exactly what I'm talking about. So this is the other way of doing it, and it turns out that you get 52.22 as sigma naught. Okay. All right, let's move into what this has to do with anything. Okay. I'm sorry this video is taking a little bit longer, but there's a lot to go over. All right. We have our failure rates right here. Now we know our characteristic strength, but we don't know our slope. All right, well, let's start inputting these equations in Excel and getting numbers back. So we're going to do this one. First, we're going to do this, parts of this. Whatever. So we have 1 minus the failure rate sorry. So we have this one right here, 1 divided by 1 minus f, and then we're going to take the natural log of it. So I'm just doing each equation in steps. Now I didn't write it correctly up here, but mathematically it's done correctly. Okay, so when I'm done, I have my y values here, and then we said that x was equal to the natural log of sigma f. That's our x value. So I have those here. So this is y, this is x. So when I graph these in a scatter plot, I get this line. Actually, not this line, this curved shape. Pretty linear, a lot better than what the other ones were that we saw online. So now we just got to do insert, whoops, you click on the data point and hit add trend line, and then you just make sure it's linear, and then you hit show equation. So let me double click the trend line. There we go. So linear, display equation on chart, and if you want to know how accurate it is, do the r squared. We're roughly 91% accurate. So most of the error seems to be right here. But still 91%, that's good. Almost 92%. Okay, so now we have the equation of our line. Y is equal to 0.1625x minus 2.6779. If you have not had algebra, this won't mean too much to you, but if you have, then you know exactly what this means. So what can we do with this? Well, actually, we can do quite a bit. So let's do an example. Let's say someone comes up to me and says, hey, I want you to design something, and I know what the tensile strength of PLA is. I want to know how many parts fail at 50, I think it was 50 megapascals. Actually, it was 100 not pascals, 100 megapascals. One thing we are going to do different, though, is I'm going to use a different, I hate doing this, but not really. This equation right now, notice it's below 1, which means we have early failure. And I mean, you can see how we have how quickly things start to fail between 46 and 50. I mean, so at 50 megapascals, I mean, we're going to have 38% failure. So what I'm going to do is change the parameters just a little bit, and give me a second here. I got to pause. Okay, sorry about that. Cat was chasing the rabbit a little bit too aggressively. Okay, so this is kind of a small sample size, so I went with a much larger sample size and had a more accurate description because, I mean, look how much this varies, 46 to 55. I tightened this variance so that it was more realistic. So I actually went to school, used the tensile thing. I mean, PLA is pretty consistent, PLA plus I should say. So let me get this out. The real equation that I'm going to be using today is going to be y is equal to, what is that, 2.623x minus 18.907. Okay, notice my b, or shape parameter, is 2.6, much like the tire example was 2.5. So this matches up really nice. Okay, so what does this tell us? All right, well, let's do the example. With the data that I have now, I want to know what fraction fails at 100 megapascals, fraction, percent, whatever you want to call it. So let's say fails at 100 megapascals. Now, if you don't know why the P is capitalized, it's actually capitalized because it's the dude's name. Okay. I didn't really even think about that until a couple of weeks ago. I was just like, oh, that's because Pascal, it's a guy's name. Anyway, okay, so we know our equation of the line. We know what beta is. We know we're going to let's say 100 is equal to this is our sigma f value. I'm going to have to do an equation for this. All right. So we know that 100 is equal to sigma f. All right. That's good. So what do we do from here? Well, let's just kind of start figuring things out here. Let's say, okay, well, if 100 is sigma f, I know that x is equal to the natural log of sigma f. So let's start there. So if we actually plug that in, it tells us that x, I need my calculator, hold on. Okay, using the Windows calculator, which I never use, hopefully I did it right, I get 4.66. Whoops, 4.66. So we know what x is equal to. Okay, that's good. Now what do we do? Well, we know we have y is equal to 2.623x, which a number next to a letter means multiplication. So let's just plug that in with 4.66 because that's what x is. And then minus that 18.907, so that y is equal to, right now, negative 6.827. Okay, perfect. Now what do we do? Well, we know what y is equal to. Y, if we go up here, is equal to this business right here. So let's set this business equal to negative 6.827. So I'm just going to copy and paste that so you can see what I'm doing. Okay. Now this is being set equal to negative 6.827. All right. Perfect. What do we do from here? Well, we know how to do natural logs, but we don't know what f is. F is what we're trying to solve. This is the failure rate. This is how many fail. So now we got to solve for f. I am not going to go through that whole algebraic derivation of solving for f because it takes forever. So just know that f is equal to, let's do a new equation, 1 minus e to the negative e to the y. Okay, that's what f is equal to. All right. Now, what do we do with this? Well, we know what y is equal to. It's equal to negative 6.827. So take this number and plug it into right here, and you'll get what your failure rate is. Does that make sense? So I'll just type it out. F is equal to, new equation, 1 minus e to the negative e to the negative 6.827. Did I do that right? Yes. Okay. So this goes to solving for the failure rate of 0.00108. This is a fraction, times it by 100 to get percentage. So we're looking at 0.1% failure rate at 50 megapascals. Now, that's testing a material that had a tighter tolerance right here and was not 50 megapascals. It was, what material did I test? I don't think it was 3D printed because that's pretty tough for 3D printed material. It would have been some type of plastic. But let's just say it went up to 200 megapascals, So, and my variance was like 195 to 200. So pretty close relationship. So at 100 megapascals, that's what's going to fail, is 0.1%. Now, that's going to cover it for this video. This has been a 20-minute video. So that's one way of looking at all of this information and using mostly formulas to figure out. But in order to get this formula, you had to graph and know how to read the graph. So now there's other things like, what if you can only have 1 in 1,000 parts fail? That's where you have to work backwards, and that can get a little bit tricky. So we'll discuss that in the next video. So right now, at least you have an idea of what we're doing. I mean, 1 in 1,000, it's actually just go backwards than from what we did. So I think 1 in 1,000 is actually easier because you don't have to solve for f. You don't have to do all this tricky stuff. You can just, we know what f is. It's 1 over 1,000. So literally just, yeah, our failure rate is 1 over 1,000. So that would go in here. Now this is an actual number, and then you can graph everything else and give it a shot, see what you come up with, and I'll go over it in the next video. Anyways, thanks for watching. I know that's a long video, but it covered a lot of material. Anyways, happy holidays, guys, and talk to you later.